3.6 Evaluating specific internal energy and enthalpy. We are going to introduce a new thermodynamic property called enthalpy. We'll evaluate it using thermodynamic property tables. So first, consider a rigid closed system containing a gas. The rigid system indicates there is no change in volume, and heat is transferred to the system. Take the energy balance for the system. Q minus W equals delta E. Assuming there is no change in kinetic energy and potential energy within the system, delta E equals delta U. There is no work involved during the process, so W cancels out. So we can say heat transfer to the system equals the change in internal energy within the system. Now consider a piston cylinder device. The gas is in the cylinder. The piston is free to move and weightless, and heat is transferred to the system. Take the energy balance for the system. Again, we assume that there is no kinetic energy change, no potential energy change of the system. So delta E equals delta U. But W work is not zero. The work is done to push the piston against the atmospheric pressure. So Q equals W plus delta U. The internal energy of the gas increases and the work is done by the gas as the volume increases. So the change in internal energy of the system is smaller than the heat supplied to the system, because part of the heat is used for the internal energy change of the system. Part of the heat is used for the work. So Q is pressure times volume change plus delta U. Here note that P times delta V plus internal energy change. Enthalpy is defined as the sum of the internal energy U and the product of pressure P and the volume V. And P is the absolute pressure. The lowercase u indicates intensive property. So unit of enthalpy is kilojoule per kilogram. The uppercase H indicates extensive properties. This indicates total enthalpy. So unit of total enthalpy is kilojoule. Enthalpy can be also expressed on a molar basis, kilojoule per kilomole. If the substance is a two-phase liquid-vapor mixture, the quality is used to show the ratio of the mass of vapor to the total mass of the mixture. So the average properties of the saturated vapor and saturated liquid mixture can be expressed using the quality. Specific volumes, internal energy, enthalpy, and entropy may be expressed using a quality. So internal energy equals internal energy at saturated liquid state plus quality times the difference in internal energy between the saturated vapor and the saturated liquid. H can be also expressed in the same format. Let's see an example. Determine the specific enthalpy of refrigerant 22 when its temperature is 12 degrees Celsius and its specific internal energy is 144.58 kJ per kilogram. We know the temperature and the internal energy. So two intensive independent properties for a simple compressible substance fix the state. So in this question, internal energy and the temperatures are known. So we can fix the state. It asks to determine the specific enthalpy of refrigerant. So enthalpy is also a thermodynamic property, therefore we can determine the enthalpy of the substance. Table A7 shows the properties of saturated refrigerant 22. Temperature is 12 degrees Celsius. So first column shows the temperature, 12 degrees Celsius, and internal energy, 144.58. So here is the internal energy, and it shows the saturated liquid and saturated vapor. So what it means, internal energy at saturated liquid is 58.77. So in this plot, saturated liquid is at this point, and at this point UF is 58.77. At saturated vapor, the point sit at saturated vapor line, and UG, internal energy at saturated vapor, is 230.38 kilojoule per kilogram. But the given internal energy is 144.58. So it's between the saturated liquid and saturated vapor. What that means is that the state is a two-phase liquid-vapor mixture. So the given conditions, the given state is somewhere in between the saturated liquid and saturated vapor. So we need to determine the quality of the mixture. So the quality of mixture can be written for internal energy, U minus UF over UFG. And this equals quality is 0.5. Now we need to determine the specific enthalpy. Specific enthalpy can be also expressed using quality. So at 12 degrees Celsius, HF is here, HG is here. HFG, this value is simply Hg minus Hf. So Hf plus quality 0.5 times the specific enthalpy was calculated. Let's see on another example. Determine temperature, specific volumes, and enthalpy for water at 0.1 megapascal and a specific internal energy of 2537.3 kilojoule per kilogram. So two intensive independent properties including the pressure and internal energies are known. So we can fix the state. but we don't know whether it is a mixture or superheated or compressed liquid. So at 0.1 megapascal or 1 bar, the saturated water exists in between 417 kilojoule per kilogram and 2506.1 kilojoule per kilogram. So internal energy at saturated liquid is 417 and internal energy at saturated vapor is 2500.6 kilojoule per kilogram. And the given state is greater than the internal energy at saturated vapor. We expect the given state is located in the region to the right of the saturated vapor regions. It suggests that the state lies in the superheated vapor region. So take a look at the superheated water vapor property. So at 0.1 megapascal or 1 bar, it shows the specific volumes, internal energy, enthalpy, and entropy. And the given internal energy, 2537.3, is here. So at this internal energy, the temperature is 120 degrees Celsius. So this is the temperature of the superheated water vapor at 1 bar or 0.1 megapascal. And enthalpy of the state is here, 2716.6 kilojoule per kilogram. Determine the temperature for water at 0.1 megapascal and enthalpy 2700 kilojoule per kilogram. We don't know the phase of the water. So first look at the saturated water table. At 0.1 megapascal or 1 bar, see how the enthalpy changes in the mixture, 417 to 2675 kilojoule per kilogram. But the given enthalpy is greater than the enthalpy at saturated vapor. So it suggests that the given state is at superheated water vapor region. So see table 8.4. At 0.1 megapascal and the enthalpy is 2700 kilojoule per kilogram. It sits between temperature 100 and 120 degrees Celsius. So we need to do the linear interpolations to determine the temperature at the given enthalpy. So at temperature 100 degrees Celsius, enthalpy 2676.2. At temperature 120 degrees Celsius, enthalpy 2716.6 kilojoule per kilogram. So we can do the linear interpolation. X is the temperature at the given condition. The temperature at the given condition is 111.78 degrees Celsius.